Today I'm going to take you through the classification scheme of sandstones via flowchart example because I think it's the quickest, most efficient way to show you how we do this. You will see some occasional things from inside this book. I did write this. Let me see if I can get that piece of tape off there. And as you can see, I use it. That's why it doesn't stay closed. There is a hardcover version of this. I'll also be linked below, but I will be talking about sandstones and you will see some of the classification steps from in here. This book is not for an amateur layman person interested in rocks. It's a lot more in depth than that. This book assumes you have at least a decent understanding of geology past a 101 level class. It's a reference book. So it's not a teaching guide. That's not its purpose. So I just want to say that real quick. Now, before I get into a little bit in-depth classification and nomenclature structure of sandstones, I need to talk about other things first. Please remember, this is not an in-depth nomenclature class on all sedimentary rocks. I will be leaving out exceptions. I'm going to be talking about common main classification schemes for sandstones, and I'm going to touch on these. Please remember that, all right? This is not an in-depth lecture on the entire history and classification and sedimentation rates of all sedimentary rocks. Okay, let's get started. First, before I can get to sandstones, I need to talk about sedimentary rocks. Now, I've told you before that we are getting away from classifying rocks based on origins. This is why we don't use tillite or till anymore. We say diamictin, diamictite, which can include other till-like deposits, but we're not going to talk about those, and they will not be part of this either. However, our three main types of rock classifications, igneous, metamorphic, and sedimentary, are all orogenic in their concepts. Sedimentary rocks are derived from sediments. Igneous rocks are derived from melts. Metamorphic rocks are derived from metamorphos, igneous, sedimentary, or other metamorphic rocks. That's not going to change. We're just going to have to deal with that. Okay, you can see here I have sedimentary. We can break down sedimentary into three types of basic sedimentary rocks. We have our chemical. These would be your chemically precipitated rocks like evaporites, some carbonates, stuff like that. Now, we're going to come back to carbonates because when we get to sandstone, there's a little thing that happens and some people try to force some of these chemical rocks into sandstones. But if you are a carbonate or something like that, you are going to be one of these two. Now, wait, I just told you carbonates are here. Well, that's because some carbonates can be considered organic. They can be piles of dead things like packstones and stuff like that. So carbonates are in between these two, depending on their origin. See, there's that origin thing coming in again. Other organic rocks, coals are organic rocks. Now, I'm not going to get in an argument about how technically coal is not a rock because minerals by definition are inorganic. I've done that in another video. I will link it below, explaining why we do consider coal a rock. Clastics, this is where our sandstones are going to fall. Now, real quick, a clastic rock is a rock mechanically derived or mechanically weathered from a pre-existing rock. What does that mean? It means a rock that has been beaten down slowly over time and has become smaller bits of rock. That's essentially what that means. There's no chemical weathering, like, you'll chemically weather limestone and get caves. That groundwater will come through and it will dissolve some of that carbonate away, eventually creating a cave. So there's no chemical weathering involved here, kind of. Okay, so we have our first type of clastic rock, mudstones. There's basically two types of mudstones. You have your shales and your siltstone. Now, remember how I said clastic rocks are all mechanically derived? Siltstones pretty much are. Siltstones are a gray area between sandstone and between clay. Now, where you put that line between siltstone and clay depends on who you're talking to. We have to set a definite line though, because your smallest siltstone grains can be larger than your largest shale particles. Why is that? It's because shales are derived chemically. They are through the chemical weathering of granite and granite type rocks. They are the byproducts of the weathering of feldspars. Why are they included here? Because this is a relic from a time when we didn't know how these things formed. So mudstones were recognized to be sedimentary and were generally considered clastic long before they were known to be chemically weathered products of igneous metamorphic chemical weathering processes. So here's a hangover here, but it's based off grain size, both of these. And the whole clastic classification system is based off of grain size. We'll come back to that. Just remember, shales are finer grained than siltstones. So that's good enough for this lecture. Now going from mudstones to the other end of the spectrum, we have conglomerates. Now I'm just going to talk about the three basic types of clastic rocks here. So I'm not going to talk about diamictites, all right? I know they exist. I don't need to be reminded of it. But this is a basic concept. Sandstone is the focus. Okay, so conglomerates are basically really coarse-grained clastic rocks. They are strictly formed from the mechanical weathering of other rocks, as are siltstones. Siltstones are the smallest particles you can derive by mechanically breaking down rocks. Eventually, a rock is going to physically, mechanically weather to a certain point. It can't get any smaller. It's going to essentially be immortal at that point. And that line is below the coarsest part of this. Anyway, let's go back to conglomerates. I'm not going to subdivide these out, but these are things that contain pebbles and cobbles and boulders, even things like that. And they tend to be rounded. Now, conglomerates have also been used to describe rounded class in igneous rocks. Because of magma chambers, you can get rounded igneous rocks forming as a magma churns and turns. Some stuff will crystallize out first. As that magma cools, the rest will be molten. So you have these harder parts, the solid parts in the magma. So you can get a conglomerate looking thing in igneous rocks. However, we have stopped doing that since the late 70s, early 80s. Conglomerates now are mostly used to describe sedimentary rocks. So that has changed. So basically any rock made out of dominantly something more than a sand-sized particle is going to be a conglomerate, and we can divide those out as well. You can have muddy conglomerates, sandy conglomerates, a combination of the two. As you can see here, you have a very complex classification scheme and weird looking names that have to do with the class in the conglomerate. But this isn't a conglomerate class, so we're going to move on. So at the fine end of mechanically weathered clastic rocks, you have mudstones. At the coarse end, you have conglomerates. What's in between? Those are your sandstones. Now, you keep hearing me mention particle size. And in clastic rocks, grain size is all that matters for the basic classifications. It has everything to do with grain size, nothing to do with composition. Although we are going to break out sandstones via composition. So it has everything to do with the size of the grains. Now, generally, a sandstone falls between a certain range of grain sizes. What do we mean by that? Well, we mean the actual particles themselves of sand will fall between generally a diameter of 0.62 and 2 millimeters. I had to actually look that up because I never remember that myself. And then we have this gray area of granules between 2 and 4 millimeters. And those are a special type thing. If they're found in abundance a lot, you can put it in the conglomerate part. If they're just sprinkled throughout a sandstone, you can put them in here. That's a judgment call. And as geologists, we use the Wentworth scale. I am completely aware of the USCS and engineering scale. But in geology, we don't use it. Why do we use this Wentworth scale? Because it's a logical breakdown of class sizes. They are by specific intervals, and a very fine sand at the very bottom of a sandstone is about the particle size that the naked eye can discern without magnification. So there's a logical border there, and it's on the phi scale, so it's logarithmic, and it goes out from there, as where the USCS classification is based off industry standards. You know, what kind of sand is usually used for this purpose. So the coarsest grain sizes in USCS are bigger than the coarsest sandstones in Wentworth, and the finest are above what we would still consider as geologists a sandstone. So when I'm talking about grain size, I'm talking about the Wentworth scale. And we can have different shapes of these sand particles. We like to think of rocks as being round, but actually the weird thing is, and when you take a basic geology class, one of the first things they tell you is you don't see square block looking rocks in nature. Well, actually you do. They are actually more common than perfectly rounded rocks are. There are no perfectly spherical rocks in existence in nature, at least not at the sand size scale, but we can get pretty close. And when you're within this sand range, there is one sandstone that is considered the go-to sand to compare all other sandstones to, and that's the Ordovician St. Peter sandstone. Why is that? Because not only are the grains about as rounded as nature can do, it's about as clean of a sand as nature can do. That means you're lacking fines, because you can have fines in a sandstone, and we'll come back to that. And there are no conglomerates. And it's pretty much unimodal. The whole thing is pretty much a fine to medium sand, somewhere in that range, and occasionally medium to coarse. So it's what we call very well sorted or well sorted. And this is as good as nature can do, is the St. Peter. So that's kind of our standard. And something that is almost completely sand without any fines or any conglomeratic particles is an Erenite. Erenites are the first step in compositionally classifying sandstones, and you can see we have wackies here. So Erenites are those clean sands that fall strictly within that sand range that are lacking particles of that we would consider conglomerates, like granules, unless that's the minor part, pebbles, things like that, and they are lacking mudstone particles. They are lacking things like, clay, which makes up shales, and silt particles. Those are your Erenites. Now, we don't have anything for an Erenite has a lot of pebbles in it and granules, because you get to a certain point and that Erenite is going to become so full of coarse particles that it's going to become a conglomerate. So remember, the reason why we do these by grain size is so you can kick it to where you need to with no questions asked if it becomes past a certain percentage point. And we call clean Erenites free of muds, free of like calcareous, because you can get calcareous sandstones, things free of that are called mature. They're mature sands, as long as they are almost pure quartz. And we'll come back to that here in a minute. Your wackies have a certain amount of mudstone in them, but it's below a certain percent. Basically, wackies are going to have between 15 and around 50% fine particles, plus or minus 5% on the 50% part. Why is that included? Well, anything with less than 15% mud in it is going to be an Erenite unquestionably. It's going to be a wacky between that 15% and that 50%, plus or minus 5. Why is that? Well, because you can have sandstones that are coarser grained and might have a 50% by visual inspection volume, because in the field that's what we do. We take the visual volume in our hand lens and compare it relatively to other things like the matrix or your wacky part of this. And if the sandstone particles are generally coarser, but you have 50% mudstone, it makes more sense to call it a sandstone than it would be a mudstone, okay? And vice versa. If you have a sandstone that's about 50% very fine sand and 50% silt and clay, it makes more logical sense to put it in the mudstone part. So there's a little bit of a judgment call there at the top end of, being loaded with fine particles. So our wackies are sandstones, based off grain size, that contain 15 to 50% mudstones plus or minus. And you can sit there, if it's calcareous, you can sit there and put that in there too, because those calcareous parts are usually microscopic anyway. So those are wackies. Now your Erenites are that 0 to 15% fines. So the St. Peter has less than 2% fines in it on average, and there are some places where it's like 0.05% fine material. It's about as clean of a sand as you're ever going to see in nature. So those are your Erenites. And when you go to the beach and you look at the sand, this is what you're seeing. You're seeing Erenites. Right? You don't usually see these by walking on the beach, although these are pretty common as well. So beach sand is going to fall here. Now, we can subdivide this out a little bit more. Okay, now at this point, the term wacky is going to become the suffix of your sandstone nomenclature. You can call something just a sandstone if you want, and you could even just call it a wacky if you want. But when actually studying these things, we break them down even further. We're going to get completely away from an interpretive classification to a mineralogical classification at this point. Now, Erenites, we can subdivide a little further. Why? Because they're easy to see with the naked eye. And Erenites are really common, and they can help us understand things. When we pull detrital zircons to get source area and a maximum age, we usually look for Erenites because wackies are too fine-grained. But we can break out Erenites into silty, argillaceous, and calcareous. So our Erenite, if it's more than 0, but around 15% fines, it can be a silty Erenite, if those fines are dominantly silt. It could be an argillaceous Erenite, if those particles are largely clay. Argillaceous means clay, size particles. And calcareous Erenite, what I mean by that is your fines are mostly calcareous. And you can just say calcareous, you don't have to be like dolomitic Erenite or something like that, although you can. Now this, when I touch on this here, now if you have a calcareous Erenite, it has to be mostly clastic. That means it has to be mostly broken down from coarser rock. If you get to a point where you have too much of this, you're going to kick it into a carbonate classification scheme. Now, there have been some people who have looked at what's called oolites. Oolites are very spherical carbonate particles that are generally sand-sized in carbonate rocks, and people have called them sandstones before, but they technically are not. They are chemical carbonate rocks. So they're pulled out of this clastic system, even though oolites can fall within a sandstone particle size. And the reason for that is because if we start introducing chemically and organically dominated rocks into this system, we're going to gum this system up. You're going to start getting wacky classification systems and stuff like that. And you'll start calling igneous rocks conglomeratic or sandy or something like that. And we're trying to avoid that. So once you get to a certain point, you no longer have an Erenite, okay? I hope that made sense. Now, there is a field way to tell if you have a calcareous Erenite or even a calcareous wacky. Now, you can have a calcareous wacky, but you really can't have an argillaceous one or a silty one. We generally don't put those in there, although I guess you can. So these could be either or. But we're going to focus on the Erenites because I'm running out of space. So if you have a sand, and a lot of times they have a lot of calcareous material in them, and they'll be calcareous wackies. How can you tell if it's a sandstone or a limestone? Well, you can throw acid on it. If it fizzes, generally that means there's a carbonate component. When I mean acid, geologists usually carry around a small vial of very weak hydrochloric acid. But just because it fizzes doesn't mean it's not an Aeronite. If that fizz is very weak, the calcareous part can be very little. But there's a quick and dirty way to do this. And I figured this out in field camp and asked my professor if this was true, and he said it works. If you don't have an acid bottle and you have your hammer, and assuming your hammer isn't very messed up, because you're going to have your hammer with you, even though you may not have an acid bottle, you take that rock and you scrape it along your hammer. If it scratches the hammer, you have an Aeronite. If your question is it Aeronite or limestone? If it doesn't, you have a limestone. Why is that? It has to do with mineral hardness. Most Aeronites are made of quartz, which we'll come back to. Quartz has a hardness of around 7. Your hammer has a hardness of around 5.5, so it's lower. So that 7 is going to scratch that 5. And your calcareous part is even less, 2 to 3. So your hammer is going to scratch the calcareous rock. So just a little tip there for you if you're out doing geology in the field. Okay, I wasn't going to do this, but I decided to put these over here as well. And why wasn't I going to do that? Well, because remember, wackies have a lot of fines in them. It makes sense to call something a calcareous wacky. But if I'm close to that 50% mark or whatever, do I really need this as a modifier? It's up to you. It can help, but it's not necessary. Same thing with this, because when we look at wackies in the field, we're generally not going to be able to discern these readily. So we'll just say it's a wacky. That's the whole point of having the wacky part. But you can use them if you want. Now we're going to break down these classification of a sandstone based strictly off mineralogy. And this applies to both Aeronites and wackies. It's just if it's an Erenite, you'll do the suffix with an Erenite name. And if it's a wacky, you'll do it with a wacky name. So whether or not a sandstone is an Erenite or a wacky, we're going to classify it based on this QFL. Many of you probably have seen this on a triangular chart, ternary plot. Well, that's because there's basically 3 mineral assemblages we use to classify sandstones, divide them out further. So our first step is to break it into a wacky or an Erenite. Then we have this QFL, quartz, feldspars, lithics. And these are plotted on ternary diagrams, triangular charts, and many of you have probably seen those. Now they can be set up like the USDA textural chart, which is the one I tend to use because this has to do with texture more than not. So it would be a 3-point plot, but sometimes people set them up like you would a QAPF diagram, which you have to normalize twice and you only have 2 lines that intersect instead of 3. So depending on how simply you want to do this or your point, you can use either or. Like I said, I generally use the 3-point plot because it's more accurate for my purposes as someone who actually is trying to figure out the orogenesis of these sands. Anyway, I digress. So you have quartz as your main part, and on these charts, they're all set up the same way. Your Q is up top. That's your quartz. And sandstones that have a certain percentage of quartz in them are called quartz Aeronites. That's what the St. Peter sandstone is. It's a quartz Erenite. And once you pick wacky or Erenite, you can drop the sandstone. It's redundant. You can't, saying quartz Erenite sandstone doesn't mean anything because your Erenite tells you that it's free of fines, especially on beaches. Now, beaches that are glacially derived, like along the shores of Lake Michigan, tend to have more of this in it and this in it, but we'll come back to those. So you have your quartz Aeronites at the top. They're the peak of the ternary diagram. They're your clean quartz sandstones. And quartz on the surface of Earth, once it gets to a certain size, it will no longer mechanically break down. It gets to about, I think it's 0.02 millimeters, it's done. On the surface of Earth, Quartz is extremely stable. It doesn't react with anything chemically and mechanically. You get to a point and you're done breaking down. That's not true for these other two things. But before I continue, quartz aeronites are very mature sandstones. They're texturally mature. We call that mature. As you get these other two things in abundance, your sandstone progressively becomes more immature. And you can describe things like that. Generally, you don't put that in a name if you're naming a sample, mature or immature. But as a general description, it can be used because some things can be, you don't want to get too technical in your description. So you might say a mature aeronite or something like that, because you can have semi-mature things even if you have a little bit of these two. Okay, and or you can say an immature aeronite and imply these two are present in abundance. It depends on your scale of classification. So quartz is pretty much what you expect when you see a crystal of quartz or something like that. That pretty much transparent to semi-opaque, whitish, maybe pale gray, pale yellow quartz that's usually derived from igneous rocks as a initial protolith. Now there's other things that are dominantly quartz that can be put here or here. Now this gets complicated and we're not going to go down the rabbit hole here on this, but some quartz can be put in lithics. Well, what are lithics? Lithics, which will be on your lower right side of your QFL plot, are broken down rock fragments that don't fall in here. But I'm going backwards here because these two are closely tied together. So rock fragments, that's what lithic means, rock. So fragments of rock. Now you can have quartz that's broken down from a chemically precipitated rock like chert. Well, chert is not always chemically precipitated either. Talk for another time. Now you can put them in lithics or up here. Why is that? I generally try to put them, if I know that's what it is, up here. But sometimes, even under magnification, it's hard to tell. So you can put them in here if you don't know. Why is that? Because chert's opaque. And it's hard-ish. It can look a lot like other things if you're just doing a visual, basic petrographic analysis, which is as deep as this book goes into. We don't use, electron microscopes for anything that's in here, and you may not have thin sections to do polarized versus unpolarized. So it can be either or, and even sometimes that doesn't help. So if it's definitely identifiable as quartz, it would go up here if it's chert. If not, it goes down here. And so what else goes under here under lithics? Will be anything that's derived mechanically from other rocks, like little bits of volcanic fragments, like little bits of basalt or diabase, something like that, or a little bit of, banded iron formation, magnetite. You can have pure minerals in there too. But pure minerals would fall under lithics as well. If they're big enough to fall in that sand size range. So you can have that too, like little bits of mica. It goes here, or copper or something like that would be considered lithic. Now you can sit there and say micaceous quartz aeronite if there's, a decent amount in there, but we're not going to go that far. But what about this? You can see feldspars. Well, feldspars, if you remember from the QAPF part, can be broken into plagioclase and alkali feldspar or K-spar, potassium feldspar. But we don't divide them out here. But they're pulled out separately. Why is that? Because as a granitoid rock initially begins to weather, the quartz is going to be the last thing to weather. First thing that's going to be weathered are your mafic minerals. Your pyroxenes, things like hornblende, biotite, olivine. That stuff is unstable on the surface of the earth. So it quickly chemically reacts and breaks out. The next thing are your feldspars. We might sit there and say, well, why isn't it in lithics? Because of this thing, because of, I talked about before how feldspars are chemically derived to become shales. Feldspars almost immediately start chemically weathering as well. They're a little more resistant than your mafic minerals, but they do almost chemically weather initially. They will mechanically weather too. And we do have feldspar-rich sandstones, like the sandstones I study. There's another word for feldspar on the QFL diagram that I put there that's a holdover, and that's an arkose or arkosic, one of the two, but that implies you have feldspars. Now, some people have dropped the arkose because this word has a complicated history. We're not going to go into it here. And they'll say feldspathic aeronite, or they'll say feldspathic wacky instead of giving it the arkose name. But I still use it because it's so entrenched in the literature. So your feldspars weather next, and they will break down, and they are pulled out from your quartz and your lithics because they are generally easy to identify in magnification, because you look for the striations or you don't, and there's other tips, but talks for other times. And why do we pull them out and keep them out of this? Because they get to a certain point. A feldspar grain of sand gets to a certain point, and eventually it's going to break down, and it's just going to chemically weather and dissolve, for lack of a better term, and be incorporated into a shale. It's not going to have that continuous mechanical breakdown like quartz has until it can no longer do it. It will chemically weather before it can get as small as it can. And they're relatively easy to recognize in your sample. And that's the way it's set up. So you can have a quartz aeronite, you can have a feldspathic wacky, feldspathic aeronite, you can have a quartz wacky too, those do happen. You can have a lithic aeronite, lithic wacky. It's a little more complicated than that, but I think for the purposes herein, that's good. So to summarize in this flowchart scenario behind you before I let you go, because I think this is as far as I can go. Like I said, there's exceptions to this, there's special cases and all that, but these are all talks for other times. So in a nutshell, to break this down simply, first you have to be able to determine if your rock is sedimentary. And if it is it clastic? And it falls between that 0.062 and 2 millimeter size. And then you know you have your sandstone. And you can stop right there. You can say you have a sandstone. You can say you even have a fine grained sandstone or a fine to medium grained sandstone, because we can also break these out based off their grain size and plot those to get something called skewness and distribution, because sandstones can be unimodal. And if they are unimodal and look like a nice bell curve, they are probably the St. Peter sandstone. Not always, but they can be. But they can be skewed. They can be unimodal, bimodal, trimodal as well, these grain sizes, depending on how far down you break them. Because even though we have the standard lines, which is mostly for basic petrographic analysis, you can divide those out even further as well. So if you really need to, you can stop here if you want. Say you have a fine to medium sandstone. Be done with it. But if you need to go further, then you have to break your sandstone down into an aeronite or a wacky. And for the sake of argument here, because these are what I study, we'll say I have something with less than 15% fines. So I have my aeronite. Now at that point, when I take it to here, I'm not going to use this term. There's no point saying you have a quartz aeronite sandstone. It's redundant. Or quartz wacky sandstone. Also redundant. So now we have our aeronite, we drop this term. From here, we break out our ratio plot, make our QFL plot. And say we have, I already said quartz aeronite, but say we have a decent amount of feldspars in it. And say there's enough of that feldspar in it with only a trace of lithic particles where we have arkosic aeronite. In that case, if you have a lot of feldspars, almost no lithics, and very little quartz, you're going to have an arkosic aeronite. Some people will call it a feldspathic aeronite. So that's how you would basically break it down without going any further. And you might add to this a fine to medium arkosic aeronite. But generally, as a general rule, this doesn't always hold. And it doesn't hold in terrestrial deposits pretty much at all. But marine deposits, generally, the coarser your sandstone is in a marine environment, it's likely going to be one of these two, a feldspar or lithic. And if you had something that's done, like you can have olivine rich or glauconitic sandstones, and they would be lithics. Those things are lithics, okay? So in those cases, in a marine setting, your coarser grained aeronites are going to tend to fall here. As they become finer, those things chemically weather and become other things, or they break down further, even more, get redissolved if they're chemical. And if you have lithic fragments, you can have little tiny bit flecks of limestone in there, but as long as it doesn't dominate the rock, you're fine. But as you get smaller in grain size in a marine setting, you tend to get dominantly quartz. That does not always apply, but it's a general rule. So another tip there for you when you're in the field. Now I study mostly terrestrial sands like the Jacobsville group, the Frida Sandstone, things that don't follow this rule that I'm giving you here. But like I said, that's for marine deposits. So first you determine that you have a sedimentary rock, that it's clastic, that it's a sandstone, that it's either an Erenite or a wacky, and you plot it on your QFL. And then you name it, arcosic Erenite, quartz Erenite, something like that. And you can have in-betweens too, but here's the chart if you want to get a look at it. That's from the book. But anyway, I think that's it. I think I've covered mostly what I want to. If you have any questions or comments, please leave them below. And I hope you learned something. So just as a friendly reminder, if you see anything from this book, which I will be posting, it'll say copyright 2021. I'm not being a jerk here, but do not reproduce this stuff. You do not have permission to do that because it is published literature. I hold the copyright, so I'll do what I want. All right. So if you see that, just be mindful. I don't care if you use it for personal use, but if I see it somewhere, I'm probably going to say something. All right. I'm not going to be a jerk about it because I know people make errors. Unless you're a jerk about it, then I will be. And this book is available on Amazon in paperback and hardcover. I just had the paperback because it's cheaper, but the book is still really expensive. There's a lot in here and it's all in color. Well, except for the parts that aren't, but that I didn't set up in color. But it's all in color otherwise. So it's not a cheap book. But if you can't afford this, there are the individual ones broken out. You have Igneous, which is red covered book. You have Metamorphic, which is a blue covered book. And you'll have Sedimentary, which is a green colored book. So you can buy these individually as well. Those are not hard covered. Those are only paperback. You can probably see my UP Bedrock Geology t-shirt here. I designed this. It's available on Redbubble. I'll link it below. And it's actually really high quality. It's been through several washes already and has survived. Just note, if you do buy this t-shirt and it's not on white, it's going to have a white background. The reason why I didn't make it all transparent was so you can read everything. It's holding up pretty well, and they have other good high quality products. The thing is, they're kind of expensive. This is a UP bag. I designed this one. I also have a mouse pad that's orange and black with the UP in it and stuff like that. I didn't put anything in the middle of a lot of this because I have other geology inspired things up there along with other stuff if you're interested. The smallest silt particles can be bigger than the smallest shale particles. The largest, why can't I get this? I get it in my head, but I can't spit it out. And then it's on the phi scale, so it's law of the... Don't tell me I don't have one. I could have sworn it was in here. Huh, maybe I don't. So good Lord. Now, some people could... The finer it is... that's better.